Hey, everybody. Hello. Hi, my name's Cliff, and I'm the founder and CTO of a company called Boundary. We do monitoring, and we can talk about that later. This is not a sales pitch, don't worry. I'm here to talk to you about about a lot of my experiences having built a company, especially having built a data-centric company, and a lot of the challenges along the way, and some of the things I've learned, and sort of how I became a CTO or how I think about the role. So if that's interesting to you, then yeah, stick around. So going back, so about 4 years ago is when I started working on Boundary, mainly as a side project, honestly. It was something nights and weekends, and you know, wasn't really serious. It was an interesting project, but it wasn't really serious until we go a little bit forward. But before we get there, we built a lot of stuff. A good friend of mine, Jeff Hodges, he says a systems engineer without a good startup idea inevitably winds up doing monitoring, which, God, isn't that true? But you know, most of them end up, you know, realizing they're in the monitoring industry and they have to do enterprise sales, and so they, you know, sell to Rackspace or something, right? You know, I'm stubborn enough to actually try and make a run of this, so go me, I guess. I think there's a corollary to this one too, is that a product manager without a decent startup idea inevitably ends up writing productivity apps. So yeah, so when we started out, we said, okay, we need to focus on something. We need to sort of bite off a piece of this. And we said, okay, why don't we look at the network data? And part of the you know, the idea behind this, or the thought process behind this, was that you know, a market exists for this. We know that. So we don't, you know, we're not trying to invent a market that doesn't exist. But all the tools in that market are very ancient, and they're also, you know, they're targeted at large carriers, right? So you look at most of the network tools out there; they're hardware-based tools. They're targeted at you know, places like AT&T, and they're targeted at you know, carriers who run fiber optics and who you know, who are pushing massive amounts of data. But they're not targeted towards like the vast middle of companies that might not run that level of infrastructure but still want to have network visibility. So we started out. We said, okay, cool, but there's a problem. We're just, you know, a couple folks who don't have access to network hardware. We don't have any idea of what they're even going to put out there. I mean, we know what the schema looks like, right? We can read the RFCs, but we don't know what kind of cardinality. We don't know we don't know what to expect out of that data set as it comes in. So you know, we sort of not knowing where to start. We started out by, you know, pulling off taking an open source agent that basically used PCAP to generate flow data. And mainly, the only reason that we made that choice was because we didn't have access to the hardware. Turned out to be one of the cornerstones of the company, right? Which, the interesting thing here is that, you know, as you're going to see through the talk, all these sort of one-off decisions, they get made, and then suddenly they become canon, right? Like, it's part of what we do, right? Yes, we're software only, of course. When we started out, it was just because we were too poor for hardware. But, you know, yes, software as a service, hardware, the fall of, no, we just couldn't afford it. That's fine. But hey, it's a good thing to hang your hat on now. We ended up being lucky, right? So we took this Magi thing and we started to build around it. We started to build an ingestion engine. And so, you know, we didn't really know what we wanted to do with this. We were back-end engineers. We weren't UI engineers. We weren't good UX people. So we were like, okay, well, we can build databases and backends and stuff. So the design goal was, we got to make something that's general purpose, that's going to chew through all this data and then give a nice, pretty API to the user, and then we can see what people try to build on it or whatever, right? That was kind of the very ill-formed thoughts. Like, let's make an API that looks like Google Analytics. Not sure if anyone here has seen the Google Analytics API. The Google Analytics API, it's broken up. It's roughly broken up into a set of dimensions and a set of metrics, right? So your dimensions are categorical data, and your metrics are mainly data that you can aggregate. It's data that you can do math on, you can roll up. What we wanted to do is we wanted to make an API that looked like this. We wanted to be able to take network data, roll it up by the dimensions you see in it. So in other words, you know, being able to answer a query like, you know, show me, for the past week, show me what the latency is talking to cell phone users on AT&T, right? Like doing that kind of slice and dice, you can do that with an API that looks like that. And we thought, okay, that'd be cool. Let's try to build that. So the first revision out, and if you're familiar with HBase release numbers, you know this was a while ago. So our first revision out, we tried to build it on, it was a very naive implementation on top of HBase with an early 020 release. And we set it up, and actually we set it up on we finally got a little bit of money, mainly by consulting that we did for Basho. So, thanks Basho. But we did a little consulting, we got a little bit of money to set up some servers and set up a couple of dinky little cloud instances, and stood up our first HBase cluster, stood up this app that we had written, and we said, okay, cool. Now, how are we going to test this? Fortunately, we were friends with this man. That's Artur Bergman. He's the founder of Fastly. If you know anything about him, he makes he can generate a lot of network traffic. So that's his whole shtick, right? He runs a CDN. So he can. It was awesome being friends with him, especially at that point in time, because with a push of a button, with a turn of a key, he can send us torrents of data. And that was kind of the high watermark. We say, okay, whatever we build, if it can deal with Artur, it's going to be good enough to go into production, right? We can actually take this to market. So of course, as soon as you turned it on, first time out, it broke, fell over immediately. Turns out what happened was apparently there was a bug in that release of HBase where there was some race condition it got into where it stopped serving the meta region, and when HBase does that, it doesn't know where it put anything, so it just stops working. So we didn't even know that at the time. We found it out afterwards. We're just like, okay, cool, this stopped working, great. And it was kind of back to the drawing board for us. And really, it was, after that experience, said, okay, well, that sucked. We wasted a bunch of money on these servers. Like, what are we going to do? What are we trying to build here? Was really our big question. And one of the interesting things is, like, through this process, we didn't even know what. I mean, we knew the shape of the Google Analytics API, but we didn't know that there was a name for that, right? We didn't know that was actually a thing. It was sort of like only through sort of blind stumbling did we kind of figure out, oh yeah, it's OLAP. It's an OLAP style database, right? And it's an OLAP style query API. And once we kind of, and it seems kind of simple or stupid, like it's like, okay, cool, you have a name for it. But once you have a name for what you're trying to build, then you can actually go out there and find the research, find find like the relevant places people have failed before and try to do it better. And so once we figured out, okay, cool, we're trying to build an OLAP database. Now we can actually do the research and we can say, okay, what is an OLAP data model? It's just an n-dimensional hypercube. Okay, what the hell is what is that? But we could do the research and then we could figure it out and finally it's like, okay, it's an n-dimensional cube. So we can just simplify it to 3 dimensions. I'm sorry if that's not really readable. Doesn't need to be too readable, but basically the idea is that if you think about a cube, it has 3 dimensions, right? So you have up, down, and then backwards, or however you want to situate it. On each dimension, like if you think about like Cartesian coordinates, right? So on each dimension, there's values, right? So if you're going 0 to whatever, there's values for each dimension. And then as you go, you can basically any point inside of that cube is the tuple of the dimensions that got it there, right? So if it's 3 dimensions. It's the tuple of 3 of them. 3 values gets you a point inside of there. And then at that point, you can record all the metrics of the observations that you made. So it's essentially a way of indexing data such that you can get very easily inside of that cube. And the cool thing is that you can get subcubes, right? So you can do projections. So you think back from geometry class, if you do a projection of a cube, it's a square. But if you turn it on its side, it's a rhombus, right? Similar idea. You can do projections and slice and dice operations to this cube, aggregate things together and get a new view of the data. And that's how you can answer a question like, show me all my latency or average latency or 99th percentile latency, aggregate it in this way for all my customers who are using a cell phone on AT&T, or for show me how much bandwidth I'm using sending data to my CDN provider, right? So being able to answer those kind of arbitrary questions like that, that's really what we wanted to be able to do. And we thought this could get us there. So we did our research. And after reading quite a few academic papers on the subject, we came across this idea of, has a weird name, cuboids, minimal cubing index. And it's an interesting concept. What it is that it says, okay, if you have an n-dimensional cube, you try to build an index for all of it. It's clearly you're clearly at a combinatorial problem, right? It's a hard problem to solve. You're going to be writing much more indexes than you want to be, and there isn't enough disk in the world to index all that data. So what you need to do is you need to sort of break up the problem, and the method that we were basically trying to implement was you index it into a subcube of 3 dimensions each, right? So if you have an n-dimensional cube, say you have 7 dimensions, you do 2 subcubes of 3 dimensions and then another subcube of 2 dimensions, right? And so you can break up the problem, make it easier. And then the indexes, they get stored into a sparse table. So essentially you have a sorted table. You have a sorted table with all the values that you've seen in the dimensions. And then each of those maps to, and I'll actually show you, each of those maps to a set of records. So you can look at it this way. You can say, okay, here's a set of dimensions. And these are just zeros and ones for the sake of brevity here. But you have a set of dimensions. You have the observations you've made at that point in time. And then here's the records in the big record store. So you have a record ID, and then there's a record store off to the side. And then for the records, those are the records that correspond to that observation. And so essentially what you can do here is that you can what you can do here is that you can do set operations on these integer sets to do the different kinds of queries you want, right? So if I want to do a query where I say, give me back all the records where A equals 0, I could scan the table and then do a union on those top 2 sets. And that gives me the record set then I can stream that back from the record store and do whatever aggregations that I need to on it. So it ends up being pretty cool. And then if you're doing like a subcube operation where you slice and dice it into a lot of different buckets, each of those buckets can end up being an integer set. So you can build very powerful queries using this as a building block. Cool. All right, let's go build it. Hacked this together in about a month, which ended up being interesting. I didn't come out of my room for an entire month. I just sat there and hacked on it. But it was still a very naive architecture, right? So it was a stateless app server built on top of Cassandra. So it was this stateless JVM talking to Cassandra on the other side and say, okay, we're going to leave that evil state stuff over there, and we're just going to do our operations and talk back and forth. But it actually kind of worked with smaller data sets. So when we ran tests with it with much smaller amounts of data, it actually kind of worked. Archer still broke it, though. But the interesting thing that we found is that we could keep up with the ingest rate. So as the data was streaming in and we were writing these indexes, everything was actually keeping up just fine, which actually is kind of the story of Cassandra in general, is that the write path is great. Just don't query it. But yeah, that was the problem, is that the querying was extremely slow. And when we looked into it, we saw what was happening was that the app server was transferring several hundred megs of index back and forth over thrift. It was transferring several hundred megs of index back and forth to do the operations that it needed, even before it got to the point of streaming the records back to do the aggregations. And there was just a tremendous amount of data motion, which we all know, the Hadoop story. Data motion's bad, right? So, okay, let's move the computation to the data. Do the logical thing. We're going to embed our database logic, because that's what we're building here. So we're building a database. Let's just embrace it. And we're going to move the database logic inside of the actual database. Cool. So this is the project. This is our project we called Scylla. And we forked Cassandra, started ripping things out of it, built all new ingest and query paths. And so essentially what we had is that we had our indexing code, we had our code, our query planners, all the things that we needed to do those cubing and then do those cubing and then querying operations. We had them all talking directly to Cassandra mem tables and SS tables, and it was manipulating that code directly. We didn't touch any of the other thrift stuff or any of the other parts of it. And there's only one way in and out of the system, and that was through our query paths. And that ended up being actually pretty fast. It drastically reduced the data motion. We didn't have any remote joins, and it stood up to Archer's test. And we could query the data and actually get back reasonable results, which was like, wow, excellent. It was a good prototype. And we got and this was actually what got us funded. So we had this prototype and we started pitching it around, and people gave us money to go and actually build a company around it, which was like, okay, cool, we're going to go do that now. And that brings us to kind of, this was, and then that brings us to our post-funding era. So it's like, okay, phew, we got money in the bank, everything's fine now, right? Nope. Now we gotta actually we gotta take this and sell it to customers. We gotta make it work. We gotta build a company around it. The problem was we were having trouble scaling it. So there were problems with our design. So, and once we actually tried to test it against, someone other than Artur in different situations, we started running into these issues. Had a really bad load balancing algorithm. So one of the tricks that we were pulling here to avoid having to do remote joins was that we'd bucket the data into hour-long intervals. So for an hour, so for any customer, for an hour, all their data is going to end up on one node. Which if that customer can't, there's multiple problems with it. Like one of the problems is that if that customer doesn't fit on a node, you're screwed. Because if it's too much data for that node to handle, that's bad. But then the other part of it is that you're going to have one hot node in the cluster, and that's going to sort of candy stripe around as time goes on. It's not it's not a great scheme. We also had indexing race conditions. So one of the interesting things that we didn't find out until way too late with our bit set library is we're using compressed bit sets. With our compressed bit set library that we were using, we didn't know until much later, but it has interesting property of only being able to set the leading edge, right? So if you have, so basically if you set, if you set the number 3, you can't go back and set 1 or 2. So as soon as you set the leading edge, because it compresses everything and it doesn't do the operations to decompress. And so we ended up in a situation where we were dropping, so our indexes were silently dropping these things because it doesn't throw an exception or do anything reasonable. It just sort of ignores the operation you gave it. It was academic code. So it ignored the operations, and so we had indexes that were full of holes, and we were trying to figure this thing out. We're like, where the hell's the data going? Like, we know this isn't right. There's problems in the indexing library. And we had multi-threaded code going into it, and that was the only way we can get it fast enough. Problem is that we'd have to linearize it. The operations would have to linearize on the ordering of the set, which you might as well be single-threaded at that point, which sucked. And then, what it came down to is also the data structures in Cassandra just simply were not the ideal way for us to be storing these things, right? Like, we're building data structures on top of other data structures, and it just was slowing everything down. And kind of what we came to was that, look, if we're going to go further down this path, we're going to have to take on the engineering task of going into Cassandra and actually rewriting the storage layer, which is just like, well, hell, why did we even try this? Why did we even use this to begin with, right? And so it really was, for us it was a time for a reset. It's like, okay, this is obviously too hard, and we need to get something out there because there's people with expectations now who gave us a lot of money. Like, we have to do something. Can we solve an easier problem? And after a lot of thinking and a lot of thinking, a lot of discussion, we came upon the idea of streaming. So we said, okay, well, what if we, what if we no longer have this model of put it in a database and then query it to get it out? What if we compute everything on the fly as it happens? We can store off the aggregates into a historical storage or do something with them. We don't have to worry about that right now. But we can send the aggregates that we compute. We can send them to the browser immediately because, WebSockets exist, Longpole exists. It's actually pretty well-tread technology to do that. We can send the data to the browser, and then the cool thing is that not only is this an easier problem to solve than ad hoc queries on everything forever, it also ends up being a much better experience, right? Because then you have a dashboard that basically gets stuff pushed to it like a movie, and so you can see things as they happen on the machine as time goes along. So it's a better experience too. So not only is it an easier problem, but it's better for the user. Cool. So we wrote this thing called Streaker. This was our prototype. This was our prototype streaming system, and it was prototyped using a project called Esper. We've since gotten rid of that, but yeah, it was prototyped with something called using Esper. It was very simple, single node at first, and but the cool thing was that we demonstrated it could work. Built a crappy prototype, demonstrated it could work, and then we said, okay, cool. We think we can actually take this and build a real product around it. We thought we had something that we could scale, and so for us, that was like, okay, cool. Well, now we know the technology path. Now it's time to actually build a team and a culture around this, right? Because ultimately, that's what you take money for, is to build a team so that you can do more things and so you can build more stuff. And that's what we did. Went out, recruited a team, and the interesting thing is that team and culture and technology, they all intermix in very interesting and odd ways. Until you've done this a few times, it's like, it doesn't seem obvious with the results that you're going to get, right? And so, and the team, and ultimately the team and the culture end up building the product. Like, you might make the prototype, but the people that you hire and then the values that you instill in them that's what's actually going to build the product, as opposed to anything you might say or do, right? So culture. A lot of us startup people love talking about culture, and no one can agree on what it is or even what it means. So, I'll tell you how I use the word. It's a set of shared values, and it's extremely important in teams because culture is a distributed consensus protocol, right? And so what I mean by that, I'm a distributed systems engineer. That's the way I think about things. And so it guides decision making amongst a team without explicit direction, right? So in other words, me as a team member, I'm working on the UI. He's working on the database. He's working on the middle tier, right? Like, how do we all sort of arrive at the same place and run in the same direction without having to constantly be told what to do, right? Because there's a lot of places where it's very top down, and you get told, here's what you're working on. That you go out and do this today. That doesn't work when you're 4 people, 5 people. People need some amount of self-direction in order to figure out what they need to go do, because you just don't know. There's too much to do that you just don't know. And so, the culture is ultimately what guides people to say, oh, I'm going to take this on, I'm going to push that off till later, and I'm going to make the right decisions in order to arrive at the right outcome. And the interesting thing here is that the culture and the technology, they tend to reinforce each other, and they form path dependence. And what I mean by that is that the choices that you make early on, right? Come back to earlier on, like when we chose to use a software agent, what was an offhand choice at that point in time then became instilled in the culture and says, yes, we stand for that. That's what we do. We're software only. But that wasn't the intention at the beginning. But people rally around the weirdest things, and the culture and then the choices that you make get institutionalized. And then that's how you form path dependence, right? Because there's the theory from political science. There's this theory called the Overton window, and one of the interesting things there is that basically what this says is that as a leader, right? And this is mainly applied to politicians, but I think it applies very well here too, right? So as a leader, the set of acceptable decisions that you can make has absolutely nothing to do with your personal platform, right? So in other words, I could be a Java engineer. I could be a JavaScript engineer. I could be a C++ engineer. If my team has sort of an Overton window that is settled right around Java or Scala or Erlang, right? Like if I try to introduce C++ and say we're going to go build this in C++, or we're going to go and we're going to use this open source software that like the set of decisions that you can make, if they don't fall within that small acceptable range for that group of people, doesn't matter what your personal platform is, you're going to fail as a leader. And people are not going to accept the direction that you're going in. It's going to turn out badly. And that's kind of what I mean when you have path dependence, is that the types of decisions that you can make in the future are completely limited by the choices that you've made in the past. And see that come up again. But the early team was very much systems engineers, because we were building a distributed system, and so we had to process a lot of data in a soft real time. And systems engineers have a very particular culture. They have a set of values, right? Like a lot of systems engineers, they build big things. They've been burned by a lot of software, because it doesn't scale or because it has weird properties at scale or whatever, right? you go through the failure of so many open source projects because you try to use them in slightly weird ways and they blow up at scale, that it tends to instill some very interesting and weird values in you. And not to say that, I'm not really making a judgment call, I'm just saying these are the things that happened. And sort of looking back at them retrospectively, it's interesting to analyze what were the outcomes of a lot of cultural things that came up around the team. And one of the things that quickly became sort of ensconced in our culture was that the scale that we're working at with the amount of data that we need to be able to process, and like it breaks everything. So therefore, we have to do everything ourselves, which for a lot of components really actually was the truth, right? Like, there's a lot of things that we just had to build ourselves because nothing existed in the open source world that could handle it. And the way I like to think about this is that it's a Finnish word, sisu. I'm not sure if anyone's familiar with it, but it's a Finnish word. It means grim determination in the face of annihilation, right? Like basically, existential threat, but you keep going on anyways. So that was very much, if I could put our team culture in one word, it was that, right? Like, damn it, we're going to make this work, whether we like it or not. Became very deeply suspicious of most open source software, and we just said, okay, we're going to have to build everything in house. And so we built our own query engine. So we threw Esper out because it had problems at scale. So it had problems with memory overruns and blowups and that sort of thing. We built our own query engine. We built a distributed load balancing engine. That's actually open source. That's on our GitHub. We built a lot of plumbing, right? So I spent a lot of time building a system to make Scala and Erlang talk to each other because we had parts that we built in Erlang and we had parts that we built in Scala. And so I wanted to make them talk to each other. But all this time spent building plumbing is that it's dangerous, right? Because as a startup, you only have a limited amount of time before the runway runs out, and you have to show progress. And you don't really want to spend your time building plumbing. But basically, the culture plus the technology choices plus the scale that we were trying to work at meant that these were the decisions that we made at the time. And looking back, they could be hard to justify without the context, which is interesting. We had to build our own multivariate graphing library. So we had to basically build a graphing library on top of Canvas. Basically, it was half of a database engine internal to the browser. So part of it was that we needed to be able to do the slice and dice operations without going back and forth with without re-requesting certain things from the back end. And so it essentially had to have almost half an OLAP engine implemented in JavaScript, pushing 10,000 data points per second through the browser. That was a lot of work. But a lot of these things ended up being very high performance, and for the task that they were built for, they worked really well. So in the meantime, though, commercial pressure, right? We're a startup. We have to show traction. We have to sell. We have to have a good outcome for our investors. And the interesting thing here is that we're trying to add paying customers, and then inevitably in the enterprise world, you have to do custom work to sell big deals. And what ended up happening is that we'd have a lot of features that were gated on sort of core infrastructure work. So in other words, inside of the streaming system, we had to implement new things in order to sign up customers. And then we get into this situation where, if God forbid, if something that a customer wanted slowed things down for everyone because it's a multi-tenant SaaS system, then how do you actually make that decision? You turn the deal away? Do you, what do you even do there, right? And so all these questions came up, and we, honestly, we weren't prepared to answer them, right? We weren't prepared for this eventuality of what the commercial pressure would actually bring, because we were just systems engineers. We weren't, we hadn't done enterprise stuff before, so it was a very tough learning curve. And then, of course, while we're building all these new things, all these new features, and trying to close deals, we had to keep scaling the system and making it larger. And it becomes a struggle just to keep up with all. You're constrained on the number of people that you have. You're constrained on how much time you're spending on these things. You're constrained on firefighting. It's a struggle. So that brings us to the past 6 months, which has been sort of a very kind of like watershed moment for us. So we just had a lack of engineering bandwidth, right? So there's churn in the early team. People who've been there for like 2 years and they're ready to move on. And so we're sort of like, okay, well, buy all that institutional knowledge. Cool. Okay, how do we how do we keep these things running? And the good thing is the lack of engineering bandwidth forced us to, kind of step back and say, okay, look, we can't tackle everything. We need to reevaluate. Part of what I did was I said, okay, look, what would happen if I had to build this over again today, just as a mental exercise? If I had to take a step back and say, is there open source that I could use? Are there things that that could replace all the stuff that I already built? And maybe building everything yourself is not the best idea in the world. The danger there, of course, though, is that once you go down that path, you start to think, okay, well, we should just rewrite it. And there's no such thing as a successful rewrite. We talked about rewriting for a while, and it sort of kept nagging at me. It's like, okay, yeah, we can do all this. We can, we'll push the fires off to the side, and then we'll do the big rewrite. And I'm just like, wait a minute. It sounds so nice, doesn't it? Because someone says, oh, it's a clean code base. You can go in there, and it's going to be so much faster because there's not all that cruft. But then you think it's like, well, aren't I going to have to re-implement all that stuff, and I'm going to end up with all new cruft? And so I think that there's such a thing as a sustainable rewrite. You can't just burn it to the ground and start over, right? Because there's still that commercial pressure. You still have to sell. You still have to make your numbers, right? Like these things have to keep running. But we can mutate the system towards an end goal. We can basically pick off the incremental improvements, and we ask ourselves, where do we want to be in 6 months, 9 months, 12 months? So the goals we put out for ourselves is like, look, we want new metrics. We want the ability to add new metrics very quickly. And that was one of the big problems with our query engine, is that it was extremely static in what it would accept. That made it fast. But now we're like, okay, well, we need to add a bunch of new stuff, and we can't gate that on core infrastructure engineering time to make it happen. So how do we do that? How do we have a flexible query language so that we can get back to this, to the flexibility of an OLAP style query, right? Where it was an OLAP engine, but it was very static in what it could do. How do we push out more analytics to the edge? So we have these software agents running on people's servers. Can we have them do DDoS detection? Can we have them do security stuff? Like, there's so many things you could do if you think about it as an analytics system with sophisticated agents at the edge of it. There's so many things you can do in situ there that it'd be stupid for us not to. But nothing was set up to be able to do that. And of course, we wanted to be able to support large customers and ultimately support customers that can span multiple machines on our side, right? Like infinitely scalable, right? we wanted to support people with 100,000 machines, 200,000 machines, massive amounts of data coming through from a single customer. And so our path to get there, and we're just almost finished with number 2 on this list. So this is a story in progress, of course. Add hardware to alleviate the short-term scaling pains, right? So we still have that scale limitation of, we can only support a certain size of customer, and then beyond that, we're sort of left in the lurch. And so we sort of block and tackle to solve that. But for the short-term scale problems, let's just throw a bunch of hardware at it, and so everything sort of gets siloed off into its own little area, and so that when things go bump in the night, they don't wake other people up, right? We can identify and ship a minimal set of features, right? So we say, okay, what are the things that are going to keep sales moving for the next, for the next 6 months? How long we need to get this thing fixed, and then figure, okay, once we get those shipped, and that's coming at the end of the month, hopefully. How do we embark on the rewriting the specific, very small modules incrementally? To get us to where we need to go, right? And so how do we plumb through new stuff into the query engine? How do we plumb through the analytics at the edge? And how do we do that? By replacing pieces of the system as it's running. People always like to say rebuilding, rebuilding a jet engine in flight. I always like to say it's performing surgery on a horse in the middle of a river, but it's the same principle, right? You're in an adverse environment, things are running, but you still have to replace the parts of the machine as they go. And I think that the sustainable rewrite, looks like firefighting, where you have to find the fire breaks and contain the problem. But the interesting part about this is that from talking to other people who are talking to other people who are CTOs or founders of other tech companies, basically this is every company. So you look at a company like Twitter, you look at any of the large scale, especially consumer side, but any of the places that work with large data sets and that do these things at large scale. From the outside world, it looks like they have all the sophisticated stuff. It's like, oh, Twitter, they're amazing. They just released that Manhattan database and they're doing all this amazing work. But then when you talk to people off the record and they say, oh yeah, we have whole teams of people that just do data rewrites because we have consistency problems, right? Like you have yeah, exactly, right? And like there's so many companies out there where it's like getting the market and getting things out there quickly means the difference between survival and death, right? And so cutting the corners, and this is a thing that was very tough for me to get through my systems engineer mind, right? Where things need to be correct for me. I want them to work properly. But you know what? Actually getting it out there and being a piece of junk is going to be fine in most cases because later on you get money to throw people at it, which is awful, but it is the truth, right? And so many companies run on data entry people just to fix their stuff. They run on customer support teams just to patch things over when things go wrong. That's kind of the way business is done. I've worked in banks before where it was the exact same thing, but just didn't sink in. It's like how much money did we lose today? Only $200,000. It's no big deal, right? Like that's the kind of math that goes on in a lot of these places. And that's the state of our world. It's ugly, but it is the truth. And you always end up in a firefight, even if you embark not to get into one. So get it to market. That's the way. And so, kind of, summing things up, like how to be a CTO. This is my non-definitive guide to kind of sum up my experiences over the past 4 years. You build bad prototypes, and they're always going to be hulking pieces of junk, and just, be okay with that, the important part is to, prove out your concept to show what's possible, but then just have it in your mind that later on, when you hire people to make it, when you throw people at the problem, they're going to want to rip up and rewrite certain parts of it, and some parts of it are going to be junk, and let them do that. You hired these people for their expertise to help you build a thing. You don't want to cling to the stuff that you built yourself because it's special to me. Throw it away, and let the people that you hire to come in and build something better. You recruit and manage a team, right? You hire those people. The interesting thing about the CTO role, though, is that at the very beginning, right, you're CTO and VP of engineering, essentially. You're sort of the engineering leader. And so you have to recruit, you have to hire people, you have to manage them. Probably not too much management because, it's culture, we just go in the same direction, yeah. But mainly that's because you don't have organizational skills, or I don't at least. And so I'm no spreadsheet jockey, and I can't keep a schedule to save my life. But you can do it for like 5 to 10 people, right? Should work out pretty well. Eventually you'll promote an engineering manager. And I'm a strong advocate of promoting from the inside for this. Engineering teams tend to be very tight-knit, especially early on. Trying to bring someone in from the outside can end up poorly. So you're going to want to promote from the inside if at all possible. And basically the way that the split ends up, it's an interesting set of roles, CTO and VP of engineering, because like the best way that I've had it explained to me was by Jason Hoffman, formerly a Joyant. He said that he gave a presentation once where it said, the VP of engineering is focused on building and maintaining a team, and his that focus is, I need how do I build the best team possible for this company, and then the focus of the CTO then becomes, okay, he's got the team part figured out. How do I make sure that we have the best technology possible to get to our goals? And that's been a big part of my job over the past 6 months, is trying to taking a step back and figuring that out, focusing on the technology and say, okay, the choices that we made, go back, because when we get new people come on board, they inevitably ask me, hey Cliff, why did this happen? I'm like, well, there was reasons, but I forget, and I don't know, sorry. But what happens is that to actually go back and do the archaeology and figure out why did we do this at this point in time is revealing, because then you can actually figure out, how did the choices we make at that time, how did they help us, how did they hurt us, were they accidental or were they intentional? Because both have massive effect on you later on. And then how does the past constrain our choices in the future, right? Like how do we? But then how can we break out of that and then make a different set of mistakes next time around? Like we build something new, we go forward. How do we make different mistakes and not keep repeating the mistakes of the past? Or even if they were mistakes, like let's do the right things and then constantly refine ourselves. And I think that's a lot of what I don't know. It's a lot of what my role has been about, is trying to figure that out. But then the other part is don't put yourself into an ivory tower, lose touch with the code, right? Like you got to keep. I mean, giving talks like this are fun, but I'm going to be coding after this. So anyway, that's my experience, and hopefully this was helpful. If not, you can yell at me on Twitter. I'm Cliff. Hey, any questions?
So this might be easy to answer, but when you're looking back to try to figure out what choices helped you, what choices hurt you, what sort of artifacts are you looking at? I imagine in a startup you're kind of churning through things really quickly. You don't always have all the context into a decision that said was made like 8 months ago. So are the things that you look out for, tickets, notes, that kind of thing?
That's a very good question, and a lot of it ends up being just like archaeology, because there's IRC logs, we were not really great at keeping notes of anything. I mean, there's Jira tickets. It's spread out everywhere, man. Like it ends up in wikis and stuff like that. So for a lot of the major pieces, fortunately, I was in the room for the conversation, so I remember what we were saying at the time, which is good. When I don't, I'll just make something up. No, I mean, but I mean, if it ends up being something important, when I've sort of done these when I did this retrospective, like. Most of the important decisions I was able to actually pull to mind very quickly and say, okay, how did this happen? Oh yeah, we did that. There hasn't been a whole lot. That happens a lot more in the micro. You know what I mean? So like if it's like, why did we choose this set of aggregations over that one? Or why do we make some of the smaller decisions? Those end up being, yes, you got to go trawl through that sort of stuff. Honestly, they don't usually end up being as big of an impact as kind of the things like foundational stuff. And obviously, the further back you go, the more impact they have on ripple out into the future. It's a good question, though. Hopefully, I answered it.
So the decision not to use open source is kind of interesting, right? Or you kept it as open source. Is that because you were so time constrained that you couldn't enhance the open source, do what you wanted, or push the project, or politics in the open source community that prevented that?
I think there's, so the question was, for the sake of the video audience eventually, so the question was, the decision not to use a lot of open source is very sort of very interesting, and what were the main motivations behind that? And I think there was, it was very multifaceted, right? Because at the very beginning, we did try to use a lot of open source, but we just kept getting burned. Things kept not working, right? Like foundational bugs in like HBase, like it stopped serving the meta region. Like that's, it's like, these things can fall over so many. They can burn you over so many times, and then you say, okay, well, why do we keep going back to this well? And I think so. A lot of that, was sort of experiential. Of these things have failed too much, and obviously we're just going to have to go off and do this ourselves. But I think the danger there, of course, and we definitely got to thinking this way in a few cases, was, okay, we just assume that this is the case. We just assume that, oh, they released a database, all right, it's probably bad. We're not even going to look at it. That's a dangerous attitude to have, right? You can't just dismiss things out of hand without actually doing a real evaluation. But it's very easy to do that, especially if that has always been your experience beforehand, So I think that it's like cultural. A lot of it's cultural. A lot of it's attitude driven. But I mean, we do still use a lot of open source. We tend to use it in the micro more than relying on large projects. One thing we do use the heck out of is we use a lot of React. All of our historical stuff goes into there. And what we have tended to use is the things that are a bit more don't try to be fancy, just because we've always gotten burned when stuff tries to get fancy.
You mentioned that you're going to be coding after this.
Probably, yeah.
How do you balance your coding with your other duties?
So if no one's bothering me, then that's what I'll be doing. But if something, if something, I end up being sort of interrupt driven. One of the things that I've gotten extremely good at is context switching, which is a really hard skill to do. So I can switch in and out of the code pretty easily now. I used to not be able to do that. It would take me a week it used to take me like a week to switch from manager mode to coding mode. I can do it in an hour now, which is pretty good. But it was a very long and tough, arduous process to sort of get there, and a lot of it ends up being interrupt driven. It's like, crap, this is on fire, blah blah blah. You got to go visit a customer and go and give talks, and so I end up being interrupt driven, where like these weird things come along and I have to go and take care of them. But then I can come back and get back in the code pretty quickly, as long as it hasn't changed too much since I last been in it. And so as long as the distraction ends up being short, it's easier, right? Yeah.
Do you have any tips on managing the feature set of some of your larger enterprise customers and some of your other customer base?
Yeah, no, that's a great question. A big part of so I didn't. So I apologize because I didn't go into a whole lot of the motivations behind that sort of list of goals that we had. And for a flexible query language, the big idea behind having that goal is that one of the things I've been worried about is that we have all these high performance systems that that are processing data and like they're soft real time, right? They have to keep up with the wall speed. So one of the things there is that if I'm thinking about where are we going to be a year from now, 2 years from now, if I'm scaling out that team, how well does a core infrastructure team scale? The answer is not very well, just because it's a rare skill set. Those people are relatively expensive, and this is a startup, and we have to pay people well, and it's you're money constrained, right? When it comes down to it, and so you can't scale that team out to be gigantic. So how do you leverage that team out? And our answer is that, and this is the way a lot of companies answer this question, is by transforming the stuff that Core Infra works on into a self-service platform, right? And this is the answer that almost every company will give you once they figure it out, is that you have a relatively smaller team, and their job is to basically work on and scale this one platform, and they don't get bothered by customer requests. Nothing gates on them. And then the platform that they provide provides the flexibility that then product engineers, sales engineers, and then field engineers can go out and use those capabilities of the platform to do custom work for customers and to do the weird one-off stuff. But the Core Infra never really needs to deal with it unless it breaks things. But ideally, Core Infra never has to deal with it, and then you can keep those people focused on scaling, focused on systems, and they're not moving at like a quarterly pace. You know what I mean? Like they're not getting whipped around by, this hot deal came in and we got to do this, right? Like that should be the goal of having a platform is you can have sort of a different release train for different groups because they have different goals. So. Nothing else? Okay. If anyone wants to come grab me later, I'll be around. So, thank you.